great logo, actually.
Okay, we're ready.
Okay, so I would like to welcome everybody for attending this session. The presenter today is Federico Balaguer from Digital Stream. He's a new partner from the RUC-APS project. So in this last year of the project, Federico is going to be linked with Internet of Things aspect and sensors connecting to agriculture stakeholders in Chile, Argentina, the UK, Spain, France, Italy. So it's a quite interesting involvement for digital stream in this context. So today, Federico is going to talk about AgroSemantics, Internet of Things datasets, agronomic decisions. So the idea is that Federico will talk for around 25 minutes, and then we can have an open round of questions and discussions. So Federico, thank you very much for your time and willingness to present your work. The floor is yours.
Okay, thank you very much, and thank you, Jorge. Thank you for all the attendees, and it's really nice to have time and space like this in Zoom at least to share what we are passionate about. So next, please. So talking about our motivation, it's about helping farmers to get important information on time so they can make the right decision. So this picture shows the deposit. If you are going to get a message saying that you just passed the last rest area and no U-turns allowed in this highway, it's better to have this sign before the rest area, right? Right now, at this moment, when you see this sign, your decision space is pretty much reduced to a minimum. So it is good. So this is a simple example that it's good to have some information beforehand to improve the decision making. Next, please. So in following this example of getting news or bad news beforehand, I take this example from one of the projects that we have with a Kiwi producer. He is an organic farmer actually, and imagine that driving back home. He lives 80 kilometers away from his crop. There is a sign in the route saying, the highway saying that caterpillars were found in the crop yesterday. And you know that since COVID-19, the remediation for that, which is BT, Bacillus thuringiensis, takes 2 weeks to get to the farm. So he knows at this time he's pretty much done. I mean, he's at least the first generation of butterflies will live in his crop until he gets to he gets the order of the BT. And now consider that this is a sudden early warm summer, which is warm summer is when the butterflies pretty much mates and create lay the eggs. So knowing this information about the warm summer or early warm summer will help him a week before this sign to make some decisions. I mean, there are a bunch of options other than the BT to prevent this. Or even if he knows this 2 weeks before this sign, he will actually get the product on time to fight the caterpillars. So this is just a simple example how decision making is and it's a timely fashion business. So it's important for farmers to get this information on time before, and it's actually in a way that is easy to consume. The information needs to be easy to consume. It doesn't help him to have a spreadsheet with temperature, humidities, and all the reports that generated by weather stations. What he needs to know is one specific thing about his crop and the weather in this case. Next, please. So Digital Stream, this is our company, is a small technology-based company from Argentina. We have a lot of experience working in the area of Internet of Things and industrial Internet of Things. That means dealing with data acquisition problems, sensors, different kind of sensors. Of course, the sensors that you are most used to are probably temperature, humidity, pressure, but we also have experience with light sensors, UV, and different gases as well. And also the business of Internet of Things is data streaming, cloud computing, fog computing, different communication schemes, and a lot of technical stuff that is going to be boring to you, but also, of course, we love that part of the technology. That is what we do. But since we were trying to apply Internet of Things devices to help farmers, we start to think, well, why the farmers need this technology? In what way we can deliver information that will help them to improve the decision making? And this is why we are working since 2 years ago on ICT and agriculture. This mixture of technology and agriculture, and this is where AgroSemantics was born. I mean, the idea of getting information, useful information for farmers on time. And as we show you now later, we do aggregation and risk assessment based on the data. Please, next. So AgroSemantics, it's really a combination of a bunch of things. As I said before, datasets. Datasets are collection of data coming from sensors that we know about sensors. We deliver sensors, but we can use other kind of sensors provided by third parties, and cloud sources. This is, for example, weather information or other kind of information that come from the cloud. And also we have other modules that live in the cloud. So that is cloud storage and cloud computing. And this is a very important part of AgroSemantics, but this is where the crunching number part. And at the end, we have a presentation in a part, and this is based on a mobile application. We are developing a mobile application that mainly is based on calendars. We use calendars to display this information in a fashion manner that is really easy to understand. Next, please. So I will show you in the next 2-3 slides how AgroSemantic app, the application, looks like. And this is the first thing that the user sees on the application when the application is launched. So what we have is a collection of data sets. And for every array of sensors, for example, he will have a data set. So if a producer has, let's say, 5 greenhouses, and in each greenhouse it has an array of sensors like temperature, humidity, light. He can have a sensor of PM, like particles measure sensor. that all those sensors will be a data set, plus the cloud/service sources, as I said, and the algorithm that compute all the information for that data set. And for each data set also, they will have different algorithms for computing aggregation and risk assessment, and also the alerts. So in the next slide, I show you what we have for aggregation. So aggregation is a computation that takes a period of time and computes the occurrences of an event. So for example, take cold weather. You know, kiwi crops needs around between 600 and 700 hours of temperature under 7 Celsius degrees during the winter to get a good amount of flowers. Of course, this is very important because flowers become fruit, and then fruit is what the producer needs to get to the market. So knowing the amount of cold weather hours early in the winter, and also forecasting that to spring, it's a early indication of how the production will be at the end of the summer. Another example of cold weather is oranges, which is quite different. I mean, oranges require less than 12 degrees to change color and sweeten up. So again, a farmer doing citrus oranges, let's say, will have an estimation, a good idea of, based on the weather, when he will be able to get to the market with his products. Another example of events is counting the hours that a pollination based on bees could get in a given time. You know that bees have a range of temperature where they are active, but there is another narrow gap of temperatures where the bees are actually do the pollination. So if you trying to use bees, you are really dependent on the weather and the light, actually, to know how many hours of pollination you will get out of the bees. And this is very important because, well, for example, for the kiwi producer, he rent the bees. He rent a bunch of boxes with bees for so many time, and then they after that time they collect the boxes and the bees, and then the pollination should be done. But for a tomato producer in a greenhouse, she bought the bees, and the bees long at last as 3 or 4 weeks. So if the weather is not good enough in those 3 or 4 weeks, she will need to do something else to get the pollination done. So what we have here in the right part of the picture is a calendar-based display, where for each day we are showing the accumulation of cold weather. This is for kiwi in Miramar. And the big box that we have, when the 30 number, that is the September the 30th, and that was last year. It was a really good number. They got 832 hours of cold weather, which is really, really good. I should say that all what we talking about bees and kiwi, this is work of we done in another project with INTA. INTA is the Instituto Nacional de Tecnología Agropecuaria of Argentina. And we are really happy to work with them and share this project with them. So every time that I have the opportunity, I mention this because they are great. So next, please. So about risk assessment, this is a different kind of algorithm. And this algorithm computes a sliding window where whenever an event is present. So for example, take that a gray mold develops under temperatures between 18 and 23 degrees, and the humidity between 75 and 95 percentage. So, and at least what we are thinking, what we are looking here is for a window of 4 hours of those conditions. So as soon as the temperature, the conditions, actually temperature and humidity gets inside those ranges, we start counting, and when the amount of hours gets to 4, then it's a big risk. I mean, we are pretty much sure that the gray mold is spreading in this crop. We have done this with a greenhouse with tomatoes and ají, which is the hot version of the peppers. And what we are showing in the right part of the screen, the slide, is exactly that. So there are 2 days and different colors depending on the risk. So at the beginning, as soon as we see the condition, we have a yellow bar saying, okay, this is the condition. And then when we get to the second or third hour, we say, okay, this is orange. This is pretty much at risk of having this. And then the red is absolutely, we have more than 4 hours of this condition. Of course, I don't expect the farmer to go run and do something with the mold. Doesn't work like that. But he can know, he can see what happened in his crop in the last few days before, actually, his historic calendar, so he can see a year or so of what happened. But also with the forecasting, we can show him what will happen if the weather conditions are those expected by the weather forecast. And the same thing happened with the white mold. And for the same period of time and the same data set, this algorithm will compute a different color schema, I would say, for white mold, right? And so every one of these are different algorithms that use the same data but computes a different risk. Next, please. So I don't want to take more of your time, and pretty much open for your questions. So I will wrap up now. My take on this is there are a lot of resources to help farmers to produce good decisions, and this can be applied. This should be applied at all scales. We want this information or this technique to be used for all farmers, all sizes, and this is very important for us. And those resources are data sets, that we have more data sets around that they are really used, and agronomic research. There are a lot of papers talking about really specific information about how these molds, how these insects, how these butterflies growth or spread, or good things about plant, but things that can damage a crop. And there is I think there is a missing element which combine both, and we hope AgroSemantics is at least one of those things that combine data sets and all the agronomic knowledge that we have, and keep growing in a simple manner that can be used for a lot of people. So AgroSemantics is really a platform that can be useful to academics performing new experiments. And this is, of course, an invitation for all the academics performing experiments to work with the tool, with the platform. practitioners creating custom algorithms for some clients of what they have. And of course, farmers using semantic tailored information to improve his decision making opportunities and be more efficient on production. Next, please. And this is the end of the talk, and we are happy to answer the question that you will have. But of course, if you can do, come up with your question, or you can pick one of these list of questions that we will be really happy to answer. So I quiet now and listen to your question. Thank you. Thank you very much.
Good morning,
Thank you very much,
Federico.
Federico, for all your comments and information. It's been very useful. Of course, I would like to open the question to anybody from the audience before I make my own questions.
Good morning, Federico.
Horacio, are you there?
Yes, can you hear me?
Yes,
Yes.
very well.
Hello,
Okay,
Horacio,
thank you very much. Fine, and you? Thank you for the presentation, Federico. I would like to start with the question number 1. It's very interesting to me. And
Thank you.
AgroSemantics. Thank you.
Okay. Okay. Right now we are still developing the application. We hope to have so we are developing the application. So it's in internal use for now, and we will be opening for beta testing in the next few months, I would say. Alejandro is part of this workshop, and he can probably answer better than me in that area. Alejandro is also a partner of Stream working. We are working together. Alejandro, when people can download AgroSemantics?
Hi all. I hope the app will be ready on the, at least for Android, on Google Play repository, let's say maybe during the next month. Yes, just maybe a beta testing version of the app, as Federico said.
Okay, great, thank you. So next question, if any.
Yes, hello, Federico.
Hi.
Mariana.
Yes.
I didn't answer you because I worked with some sensors from your company.
Mm-hmm.
But I didn't ask you if I can use my existing data logger.
Oh yeah. So that is question number 3.
Yes, question number 3.
We wrote that question thinking about you.
Thank you.
Yes. So there are a couple of things. The question is yes, but there are things that need to be considered, of course. We have to make sure that data comes with the frequency that we need in order to the data set to be consistent. But we can also work with batches. So data logger, the concept of data logger is a sensor or a bunch of sensors that are not connected to the cloud. And you can probably collect data for 2 or 3 months, and then once you have all the data, upload it to the cloud. We can do that. We can use that data, of course. And perhaps what we have experienced in another project is that we have to adapt the data in a way that can be used inside the platform. But yes, I mean, this is not impossible. It's something that we are thinking, that third parties connected to the cloud or data logger, so unconnected to the cloud, not connected to the cloud, can be used in the platform. So the answer is yes, but we will need to to do a little bit of adaptation of that data. Thank you.
Okay, thank you, Federico.
Mm-hmm.
So I would like to make a comment and a question. So first a comment. Thanks, Fede, for a very nice presentation from the starting point. The welcome with the music was already setting the mood for the encounter. I'm very happy that we've got Stream into RUC-APS, even though we still have 1 year, only 1 year. I'm very happy that we have them. Using data to make decisions, it's a very hot topic now. It's hot because everyone is talking about it. It's hot because we've never had so much data available, but it's also very complicated. As you may have seen from what happens in the news with data about the COVID pandemic. The data is not always available. It's not always the right data. And even when the data is available, it's not always interpreted. There is not always a right interpretation of the data. So for doing database decision, there are two skills that at least you need. One is to be able to collect, transmit, store data, and it has to be the right data in the right formats in the right time. And then there is another skill that is to be able to use and interpret this data, to know what questions to make to this data for a given domain, for a given use. And this introduction is just to say that I'm happy that Stream is here because they have both skills. They are somewhere breaching this, being able to create a sensor like Fede showed, but also being able to talk to a practitioner to know how to use that data. So that was the introduction. I'm really happy that you're here. Now the question is, now, but the question is easy. So in the example you showed that you were using humidity and temperature, or lightning, the amount of cold and light, I think, to infer or compute the probability of this fungus to appear. Now, this is one special case, one special interpretation of the data. Let's say that you start discussing with Mariana, and she has a new interpretation, a new thing that she wants to predict. How does it work with your company? Do you create a new application? Do you introduce this new prediction into the same system? Is it clear? Does it make sense what I asked?
Yes. Okay. Really good question. Yes. So it can be. We were thinking in two different aspects to answer your question. A really good question. One thing is the application that you see there in the picture. It actually has an editor where you can add new algorithm or even customize an existing one. So right there in the application, if of course you really need to know what you are doing. I mean, if you mess up with that, the results will be could be completely wrong or funny ones, you know. So that is one thing, and also depending on what is the analysis required from the datasets, sometimes we will need to change or add new behavior in the cloud computing module. And right now what we are doing, for example, we are developing a bunch of algorithm to correlate the temperatures from the weather station with different scenarios where the crops are being grown. So for example, it's not the same kiwi fruit. It develops under a net. So the temperature under the net and under the kiwi plantation is quite different from the outside, but also you can consider greenhouses where the temperature and humidity scenarios are completely different. So we can also create some functionality that is really heavy on computing on the cloud, and leave the lightweight computing to the mobile phones. Of course, today mobile phones are so powerful. I mean, that you can run decent amount of functionality there. You know, just consider that the Apollo mission that landed the first humans in the moon got a computer less power than a Palm Pilot, and the Palm Pilot was really hot 20 years ago. So telephones right now, mobile phones are almost, comparing to that, are supercomputers. So we have the ability to try to answer your question now. So we can Mariana could change or customize an existing algorithm right there in the phone and see the results right away. Or if it needs a major computation, it can be implemented in the cloud. And we are working in those two scenarios. Thank you. I think did I answer your question, or?
Yes, thanks.
Okay.
Thanks.
Thanks.
Good morning, Federico.
Hey.
Horacio here again. I would like to ask about the sensor. Do you manufacture the sensor, part of the sensor, or do you obtain from another provider? Thank you.
A really good question. Well, of course not. We are not developing individual sensors. If you take one sensor, for example, temperature, we do not implement the sensor. We buy the sensor out of the shelf, and we have a lot of experience picking up the right sensors. It's quite common, you know, the kind of sensors people use with Arduino, for example. They're really shaky, and they don't last very long in real conditions. So for example, we have a lot of experience with sensors, humidity sensors that go crazy with a little of exposure to real humidity in the outside. They go up to 99%, and then they do not recover. So picking the right sensor, particular sensor, is a very important part of the job, as you probably know. But now what we have is a platform. FlareSense is our platform where different kind of sensors can be integrated and managed and collect data, and then FlareSensors is the one who takes care of sending that data up to the cloud, or even we have a simplified version, thanks to Mariana, for testing our first version of that, which is just a data logger. So it logs into a memory card, and then you, after a couple months, you take the card and then you recover your data. So particular sensor, like I do not manufacture the UV sensor, but I know how to integrate UV sensor with FlareSense to get the right data out of the sensor, and then upload that to the cloud. Same with, you know, we have a bunch of sensors with which we have experience, you know, PM, like particles, gas, like ethanol, or, you know, all kind of atmospheric sensors. that are really hard to use. And if you don't know how to get the data out of them and how to use them, you just destroy the sensor, or even worse, the data that you get is completely useless. So that's why, well, here part of the session is Juan Lucas Gutierrez, who is our electronic engineer, who takes care of that. Knowing how to get the data out of the some analog sensors is a really hard engineering job. So answer your question, we use the particular sensor out of the shelf, and we know how to test that and know which sensor is crap and which sensor is good. Sorry for the crap. And we integrate that with FlareSense. FlareSense is the other product, which is the Internet of Things part of our company, to create what I said before is a sensor array, right? It's different sensors. That is what we do. Did I answer your question? Yes. Okay. Any other question?
Yes, I have a few questions.
Yeah, Jorge. Yes.
So thank you, Federico, for all this. I think it's very useful. So what is the major challenge that you can tell us from your experience to integrate sensors in agricultural environments?
Communication is a big issue. If you want to get your data as an stream, and this is why our company is called Digital Stream, it's a big challenge. For example, in Argentina, it's quite common not to get cell phone signal to get to the broadband and push it data to the cloud. So communication is a big issue. Also, of course, sometimes the things are remote places. So another big issue is energy supply, and it is very important to get the energy supply running for this device for so many months and know how long it will last, and then package put the batteries, if you need that, in a package that it can handle extreme weather conditions, right? Cold, rain, snow, whatever, hot. I mean, if you put something inside the box and the box goes up into a tree, I would say, the temperatures inside the box is going to be really hot. So these are pretty much the worst part of the things that you need to consider, because of course if you deliver something and it fails, you're done. I mean, it's really hard. It's really hard to recover from that, from the data lost. So that is kind of the things that concern us when we are developing the sensors.
Yeah, there is a concept that you mentioned that is very critical, which is about energy. So what do you mean by that exactly?
Oh, I'm sorry. Energy, pretty much it was how to power up the device. So in the early times of the Internet of Things craziness, and everyone wanted to do Internet of Things and smart cities, was, I don't know, 5 years ago, it was the big hot thing. Everyone said, okay, we can use the box with a solar panel, I would say, and this will be the infinite source. You know, how many times we heard that the sun is the infinite source of energy, right? And it, you know, the sun will be there for a while, I hope, and it will be provide, kind of free energy. But the problem is when you deliver these boxes, I would say north of Europe or southern part of the America, for example, you don't get enough sun during the fall and winter to power up, to charge the batteries of your device. So your device will slowly not recovering from the usage of the energy he has stored in the batteries, and it will end up dying, and it's a really hard situation, So for example, we were working with a Germany company a couple of years ago. Then they tried to deploy boxes in the north part of Germany, and the problem is that they discovered that these Internet of Things boxes were failing because the sun was not delivering enough energy for the panels to power up the devices. So that is what I meant with energy. Of course, you can put a big battery, but then it will be, it makes your package useless, too big, too heavy. And our goal is to have technology that is easy to replace. I mean, the easiest possible to replace. Our boxes are made of things that you can get almost in a electric workshop, and the components that we use are out of the shelf. Of course, we put them together with enough care that we know that it will work, but it is cheap to replace, and they will last as long as we need. We don't need a sensor to last 5 years if you are collecting data for something that runs for 1 year, like a kiwi crop or a greenhouse that works for 8 or 9 months of the year. So we are conscious about that, and we are trying to use the right combination of technology for the problems that we are facing.
Well, I think that is very interesting, because normally nowadays we think in adding sensors everywhere, collect data everywhere, but it's true, they need enough energy to work. And because of course we can put sensors in cities, so we have the smart cities, but when we talk about the agricultural environment, I'm thinking like how can you maintain this in the middle of the field where there is no electricity, there is no connection, it's very far away, it's very, it's not very accessible.
Mm-hmm.
So how do you see that is the future of Internet of Things in agriculture to make it more affordable and sustainable for agricultural people?
Yeah, well, I'm not really good at prediction. I was a PhD student in the University of Illinois when I got an email saying, yeah, there is this thing called Facebook that allows you to connect with old friends. And I said, wow, what a silly idea. Who will want to spend any time with Facebook? That was 20 years ago, probably. And now,
I don't use Facebook,
I know, Jorge,
anyway.
you are not a Facebook user, but the rest of the universe seems to like it. And my first reaction was like, wow, this is stupid. So I'm not good with predictions, but what I know is actually have the opportunity to meet some, it was Angelo in the RUC-APS from Italy.
Yeah, Angelo Parente.
Yeah, exactly, Angelo Parente. And he was really open about the technology that we're using, and their sensors were really, really expensive. I mean, incredible expensive. The whole infrastructure was really, really expensive. And we sat with him say, okay, let me show you, let me understand what is this thing. And you're using really expensive technology prepared to to work in different fields, like collecting petroleum from overseas or in the seas, the platforms, the sea platforms, and really expensive things. So one thing that I think is for sure that is our take on that is use the right technology, knowing that you will in the case that your sensor is far away in the field, you put the sensor knowing that it would last 1 year or 9 months, and then you schedule that, and you know that in 8 months you will go and replace your sensor or your sensor array with a new one. And the point is, the technology needs to be cheap enough that you don't care that you're replacing that. That is the point. The point is not the cost of the technology. The point is the value of the information you can compute out of the data of your sensor. So that is the equation that we are trying to sort of understand and and get that. There are different right now. There are technology solutions out of the box to connect to things that are far away, and those are ad hoc networks. And probably some of you know about LoRaWAN, which is a particular technology and protocol to connect things that are far away, and it is efficient in terms of energy consumption. But there are other technologies and other solutions. So my guess is technology will always be available to get that sensor out of the field. And the thing is, you need to know the cost of implementing the sensor, the technology in that particular case, how long it will last, make sure that lasts as long as they say, because there are a lot of experience with early Internet of Things applications that were not lasting. Sensors were used in the wrong way, and instead of lasting 6 months, it lasted 6 weeks because they put the sensor in a box under the sun, and pretty much the sensor were working out of the range, the particular range of temperature. So the sensor destroyed after that.
Yeah.
So it is getting a solution out of the field. It is not easy. It requires engineering. And part of the engineering is knowing when to replace it and how is the overall cost of that. But and also part of the engineering is knowing what value has the information that you get out of the whole thing, right?
Well, that is super interesting. Actually, what you mentioned is I think that is super interesting because, for instance, I had 2 questions actually based on what you said. Does every sensor have the information about when they are going to stop working, for instance, because the life cycle is reaching its end? So, for instance, if you put a sensor and the sensor tells you, hey, look, this sensor is 5 years old, in 2 days more it's going to be dead, or the sensor is just get lost and then you just don't know what the sensor is because you lost the connection because the sensor is dead.
Yeah, it really depends. The basic sensors, like the analog sensors, I mean, if you have a sensor that gets the temperature, represents the temperature as a variation of current, for example, it is pretty technical.
Yeah.
That is what we call it. A very simple sensor. It will just stop working, or even worse, it will get wrong information. So the temperature sensor will say it's 25 degrees, and you know that somehow the real temperature is 12. So the sensor is just getting producing wrong data. Is the same happened with the sensor I mentioned to Horacio early in one of his questions about the sensors that humidity sensors that for some reason they got too much humidity, for example, under rain conditions, and then it will never recover, and it basically dies. And when you ask when you collect the data, it says 95% forever. And so that is the situation. And what we do is, for example, we tend to use double sensing. I mean, if we have a temperature sensor, we tend to put two sensors. And of course, also when you buy a sensor, and this is the quality of the sensor you use, they have a specification, and they will tell you how long it would last. So for example, the sensor for different kind of atmospheric gas, the specification tells you this sensor, as soon as you start using it, it will last 6 months. And if you use the sensor in the right way, with the expected parameters,
I see.
If you use that, it will last 6 months. So you know that it will be 6 months. You had to get ready to change that at that time, because you know it will fail. And this is also interesting, because your question is very interesting. This is why I mentioned that the concept of data set is not only the data coming out of the sensor, out of the box, out of the sensor, it's a data set. No, we have ways to know if the information that we are getting is off, and we're trying to find those places where this sensor it doesn't look right. This information cannot be right. Like silly example with the humidity. It rains, and then we have another sensor, or we have the weather information, detailed weather forecast for that region, and it stopped raining 2 days ago, and the sensor is still saying 95%. Something has to be wrong, and we have ways to see the data and find kind of off things that are not right.
Okay, Federico, thank you very much for your presentation and for your talk. I invite the audience to keep talking to Federico if you want. Right now we have another session, which is with Serviverde, which is a farmer which works in La Plata. So I would like to thank you again, Federico, and thank you for joining the project. And we hope that after this pandemic, we can see you in Europe and the application of your tools.
Thank you so much. Thank you for your questions, and I hope to keep working with all of you. Thank you.
Thank you very much.